This topic, as Peter just said, is new to me. I have been, for the last 30 years, designing concurrent algorithms. And of course, when you design an algorithm, you also prove it correct. That goes without saying. But proof, I would do a pen and paper proof. And but this verification business, generating or producing machine certified proofs for concurrent algorithms, is a very new enterprise for me. So I'm very excited to talk about it for 3 hours. One thing that makes me very uneasy with any talk is that it is for 20 hours or at the most 50 minutes. And such time limits are very restrictive, I feel, for me, because I'm a slow talker. And so the 3 hours you gave me, Peter, seems like eternity for me, and I'm grateful to you for that. But we will see if that will also turn out to be restrictive. I hope not. So anyway, the talk, the title, I wanted to display it again because the title said Machine Certified Proofs for Concurrent Algorithms. Why concurrent algorithms? Well, there's a multi-core revolution. Why multi-core revolution? How did it come about? Came about partly because of computer hardware. So for a long time, for many decades, the transistor sizes scaled down exponentially under constant power density, as a result of which clock speeds could be increased explosively by the engineers, by the architects, and the uniprocessor speeds were also increasing correspondingly, and that was all great news. But at some point, I understand that physics said this cannot happen forever, and the clock speeds kind of stayed the same. They were not able to be increased continually forever. And as a result, you could not expect much speed ups anymore from just the uniprocessor. But nevertheless, the world keeps needing more and more computing power. So how are you going to get that? By having multiple cores. So the number of cores that machines started to have has risen explosively from the time the clock speeds toned down. So there we are, having to face multi-cores. And it's not having to face, it can also be considered, of course, a great opportunity, a great opportunity to design algorithms. Our aspiration can be, let us exploit the multi-core machines to design very fast, scalable, and reliable multi-core algorithms. Reliable, of course, is the emphasis of this talk. So that's the aspiration, good aspiration, but the aspiration is accompanied by exasperation too. And the exasperation is that the aspiration is way too hard to achieve. Well, why is it hard to achieve? What is so bad with these multi-core machines that makes this aspiration a hard to attain aspiration? What's the challenge? The challenge is the asynchrony of the machines. Asynchrony simply means that the various cores, the programs that are executing at the various cores can be, their relative speeds can vary for a number of reasons. And as a result, for instance, even if you just have a program where just 2 processes are executing the program, and let us say you agreed a priori that the 2 processes together will execute at most T instructions. But the 2 processes, their instructions can interleave at each instruction. For instance, the 10th instruction can be by process 1 or by process 2. So you have 2 choices to schedule at the 10th step. So there are 2 to the T possible executions of length T. So there are exponentially many executions that you have to worry about that can arise. And in fact, it's not that, when you have a typical program, a process is executing the program forever. So it's executing an unbounded number of steps, let's say an infinite number of steps. And so how many interleavings do you have? Uncountably many infinite executions. And what makes design of concurrent algorithms hard, multi-core algorithms hard, is our expectation that in each one of these potentially uncountably many executions, in each one of them, the correct thing should happen. Whatever that correct thing is the specification for the problem. So the specification has to be met, not just in some or most of these executions, but we generally would want that specification should be met in every one of these executions, and that is hard to achieve. So that's what makes things hard, and therefore subtle race conditions. What is a race condition? Something that goes wrong because some execution that you did not plan for has manifested. Right? Why did you not plan for it? That it was not your plan not to plan for it. You wanted to take care of all executions, but it escaped our intellect. And then race conditions happen. And race conditions do happen. It can be catastrophic. It can be very bad, possibly even catastrophic. For instance, this Mars Pathfinder is a famous example where I understand that because of some priority inversion issue in the concurrent code, the rover crashed, jeopardizing the NASA mission. And in 2003, I understand that there was a blackout in the Northeast in the USA. Why? Because of the energy management system, there was a race in the concurrent code executed by the energy management system, as a result of which 45 million customers lost power in New England and Midwest. And this is tragic. This Terak 25 machine, again, because of a race in its concurrent code, administered 1,000 times stronger dose than what the doctors intended to give the patients, resulting in some deaths. So managing concurrency is hard, and when it is not managed right, it can lead to bad outcomes. Some can be really bad outcomes. So what is the way out? The way out, of course, is to be one thing. There are many things that have to happen for us not to get into trouble. And one of the many things that must happen is that the underlying algorithms have to be correct, have to be designed correctly. To be convinced that we designed them correctly, we will have to prove them correct. And to be convinced that our proofs are correct, the proofs will have to be rigorous. Right? So rigorous proofs of correctness for the underlying algorithms is, of course, what we would like to see happen. But what is a rigorous proof? What do we consider a rigorous proof? For instance, as I said, my 3 decades of my life were on designing some concurrent algorithm or the other, thanks to interest in concurrent algorithms that was generated by, I can name about half a dozen people who were very responsible for me to get very interested and involved in that, and one of them is Morris. And they all don't know that they were responsible, but now he knows. So anyway, what do I do when I design an algorithm? When I design an algorithm, I give it a proof. But the proof that I give, or the proof that most algorithms designers give, I think falls into one of 2 styles. One style that I would call an operational proof of the algorithm. And the operational proof of the algorithm has the following flavor. You make some observations about the algorithm through, call them observations, call them lemmas, call them whatever you want, but there are some observations about the algorithm. You say, as you can see, this is happening with the algorithm, this is happening with the algorithm, this is happening with the algorithm. And then you prove a bunch of lemmas like that. They can be 10, 20, 30, whatever, depends on the complexity of the algorithm. And each one of these lemmas is kind of argued operationally, saying, oh, look, I mean, that's happening, but when that is happening, this cannot happen because that variable has this and this variable would then have that or whatever. So born out of the intuition of the algorithm designer. And then those arguments are, of course, as good as the designer of the algorithm sees the depths of the issue and is willing to and is able to explore and explain and describe to the reader. And sometimes, I mean, there is such complex, I mean, interleavings and so on, that it is not too uncommon for some important races to skip our general our proofs in that style. And of course, I mean, if the designer made that error, if the proof giver made that error, while of course, I mean, anyone might be able to catch it, it is not too likely that someone else will catch it either, because these proofs typically run to 10, 15, 20 pages. I mean, they're capable of that. And then typically a reviewer also gets tired at some point. I mean, we are human beings in the end. And when the author himself, herself says, this case is obvious, we are willing to kind of buy that and move on. And that case probably was not as obvious as was conceived. And then there was a subtle error behind all that goes uncaught. Okay, so that's one style. Another style is an invariant style, invariant-based proofs, where you write the invariant, a precise invariant that this algorithm satisfies. But invariants tend to be tend to be meaning, I mean, they will have to be very, very detailed to be useful and to be provable by induction. And therefore, they get into very gory detail, and then they state that. And so those statements seem almost like, I mean, statements not for the consumption of a human being. But nevertheless, if you want to then prove that your invariant is indeed an invariant, it has to be accompanied by a long inductive proof, many cases of which would indeed be obvious. But there may be an occasional place where it's not obvious, but one is tempted to say it is obvious because we think it is obvious, and then keep moving. And therefore, again, it is open to fallacies. But even if you got, in the end, your invariant and you feel you have proved it convincingly, there is still a missing link. What you have is an invariant for your algorithm. What you want to prove may be some other property about the algorithm. For instance, I mean that your algorithm has the linearizability property. So you still will have to link your invariant with the ultimate property of interest, and that may again be a non-trivial step for which you might use some reasoning that may or may not be very convincing, that may or may have an error creeping in here or there. So that's how pen and paper proofs go. So what do we want then? If we are not satisfied with that, we would want machine verified proofs of correctness. Meaning, producing a proof that your algorithm is correct will still be as hard, at least as hard. But having produced a proof, the proof is checked not by you, not by a human reader or reviewer of the journal, but the proof is checked by a software system, which is specialized to check proofs. So if you are able to therefore produce a proof that you believe is a correct proof, and you then are able to feed that proof to the machine, and the machine agrees that your proof indeed proves the statement that you have fed it and said, this is the statement I want to prove, then, of course, accepting that that machine was built in the first place correctly, you can have conviction in the proof that you have for your algorithm. So that's what I mean by a machine verified proof. And that is going to be our gold standard. I think that's a great objective to have in general, but that would be what we would be aspiring for in our talk today. Okay? So, where are we therefore? We went through a few things which are that concurrency is important, multi-core revolution is happening, so we better design concurrent algorithms to exploit and take advantage of the multi-core revolution. But designing concurrent algorithms is hard, and proving them correct is very hard, and therefore we need machine certified proofs of correctness of concurrent algorithms. Okay? So that motivates the title of my talk, which is machine certified proofs of concurrent algorithms. Okay. So machine certified proofs of correctness of concurrent algorithms is a very broad topic. So among the concurrent algorithms, we would specifically, our focus would be on machine verified proofs of correctness of concurrent data structures, of implementations of concurrent data structures. So we'll spend a little bit of time on what is a concurrent data object, what's a concurrent data structure, and what does it mean for a concurrent data object to be correct, and so that the rest of the talk will make sense, but we will get to that in a few minutes. And what I will present specifically is a universal, sound, and complete technique for proving linearizability. Linearizability is the correctness condition for implementations of concurrent data structures, and I'll tell you what that is if that's not familiar to you. For now, ignore that word, we will get to that. But when I say that I'll present to you a universal technique, the word universal there means that whatever proof technique that we are going to study today is going to be applicable regardless of the type of the concurrent data object that you are implementing, whether you are implementing a queue or a stack or a counter or whatever it is that you are implementing. The abstract data type does not matter. The technique can be used regardless of that. Sound means that if our proof method that we will study, that I'll explain, if our proof method says the algorithm is linearizable, then indeed the algorithm is linearizable. Right? It's not going to lie. You can rely on the fact that if the proof method certifies the algorithm to be linearizable, then indeed the algorithm is linearizable. Complete refers to the converse of that statement. Suppose an algorithm is linearizable. Is there a guarantee that your proof method will help you, will reveal that the algorithm is linearizable? Complete says yes. So if the algorithm is linearizable, the proof method will help you figure that it is linearizable. Conversely, if the proof method says it is linearizable, then the algorithm is linearizable. So the proof method is both sound and complete, and it works for any data type. So that's what those three keywords, universal, sound, and complete, mean. There is another property that I didn't put down here that's also very, very important when you have proof methods. Who is going to use your proof method to prove that the algorithm is correct? Who is most invested and who has the greatest insight for an algorithm? Clearly, the designer of the algorithm, right? If the algorithm is a great algorithm, hopefully tens and hundreds of people will develop an equally deep insight into that algorithm. Like probably Dijkstra's algorithm is probably understood, I assume, as deeply as Dijkstra understood it by hundreds or thousands of people, because it's taught in the undergraduate curriculum and there are thousands of very brilliant people. But at least in the beginning, the person that has the greatest insight into the algorithm is the designer of that algorithm. So it would be nice if the proof methods are such that they are easily usable by the designers of algorithms. And the designer of the algorithm typically, I mean, is an expert at designing algorithms, but does not typically, have a great deal of knowledge about the various, formalisms and logics and category theories and separation logics and this and that to use them to prove their algorithm. So one of the things that would be very, very helpful for proof methods is that they be easily usable and they be intuitive, they be intuitively understood and easily applied by algorithm designers themselves. And I believe that the method that I'll present has that property. It's very intuitive and can be used by algorithm designers without any special training for this logic or this theory or that formalism. Okay, so so in order to help convince you of that, what we will do is that after I present all the theory, hopefully before the break and halftime in the through the second session, we will use the rest of the time, and I'm hoping that such time will be there, to actually together interactively develop a proof for some simple algorithm. So that we all will have that conviction, yes, we can do it. Okay, so having developed the theory, we have applied it to prove the correctness of several data structures. One of them is Herlihy-Wing Q, which was an example they used right in their first paper on that defined linearizability. And it's a simple algorithm. You will see it soon. But simple, in terms of the number of lines, but it's a mind twister. I understand that Morris gives it to all his graduate students, undergraduate students, whoever takes the concurrent algorithms class, and just so they appreciate how hard it is to wrap their heads around the problem. And let's ask for a statistic. How many of your students have come back with a proof that you considered satisfactory, Morris? 0. Yeah, that's what I heard, because my daughter is a student, and she relays some of this juicy news to me. And she got that problem, and she said, oh, this is so hard. You must have thought about it. Did you know the proof? Actually, Morris, at the time, we had a conversation around that. I knew your algorithm, and I was kind of convinced, oh yeah, this is correct. I didn't have a proof in my head, but I kept thinking about it, and it put me to sleep on various nights. It was a great sleep medicine. But until I got to this work, and then we said we should prove that algorithm. And then it turns out, and I'll share this with you again, time permitting, there is just one insight, and I contend only one insight that the prover has to have. Everything else is easy, but that one insight is beautiful, and that is, I think, what is causing the complexity of the proof in our minds. But that insight itself is not hard to kind of understand or see once you isolate it. And once you have it, the proof is easy. Hopefully, we'll get to share all of these little things. Another was a snapshot object that I designed about 15, 20 years ago. The third one is a Jayanti-Tarjan union find object. That Jayanti is not me, that's my son. And this union find object found a great deal of was found exciting by practitioners. And they have found that it gives rise to a good speed up when employed in algorithms for connected components, strongly connected components, clustering, etc. So much so that very recently, meaning weeks ago, I think, when Google open sourced its graph mining library, this algorithm was there in that library, and it was employed in their shared memory parallel clustering algorithms for clustering connected components and so on. And anyway, we are happy that this practical algorithm was also verified using our method. Incidentally, we verified the correctness of the algorithm before it went into the library. There may be no causal connection, but it was nice for us to know. So that kind of wraps up my introduction, motivating what we are going to do, as well as in some concreteness, what kind of technical results we are expecting to find. So let me pause here for just half a minute to see if there are any thoughts, questions, comments, suggestions, anything. Okay. So now let's turn our attention to technical aspects, which are more interesting than the motivation that I went through, I think. So they're going to be nice. But before we go into the proof method and I describe how it all works out, let's understand two basic terms. Let's be on the same page with respect to two basic terms. What is a concurrent data object? What is a concurrent data structure, a concurrent data object? And what do we mean by linearizability, which is the correctness condition for concurrent data objects? Just those two things. Let's get them out of the way before we get into proof methods. So what's a concurrent data object? First of all, what is a data object? Well, data object is something that's very familiar to us from the first course in computer science. We have second course in computer science is typically implementing data structures, right? So what is a data object? What is a data structure? A data object has a type. For instance, if the data object is a queue, its type is queue. And what does the type tell you? Type tells you a couple of things. It tells you what operations the object supports. In the case of a queue, those operations are going to be enqueue a value or dequeue. And it also tells you how those operations behave. But it tells you how those operations behave under the assumption that only one process executes these operations, and therefore these operations are executed sequentially, one after the previous one completes, right? And what is such a sequential specification for the queue type? Simple. We know that it's the FIFO condition captures the queue behavior. Every dequeue should return the earliest enqueued value that was not previously dequeued, right? First in, first out. So every data object therefore has a type which describes its operations and which describes its sequential specification, how it behaves in the absence of concurrency when the same process executes operations on it. But then suppose you have a concurrent setting where you have a queue and then there are many processes that can apply operations on the queue. How should this object behave? Well, what would your aspiration be? I think it would be terrific if this queue object behaves like an atomic queue. What do I mean by that? Even when many processes apply operations on it, each operation applied on it takes place instantaneously and gives a response back. Wouldn't it be wonderful if this is a concurrent queue? Concurrent queue meaning one that supports many processes, where every operation by every process happens instantaneously. That would be wonderful, but that's just a dream, right? You cannot have an atomic queue. Hardware might give you the illusion of supporting atomic objects of some simple types like read and write operations or some other simple operations. But when you have a data structure like queue, it's wishful thinking to think that hardware would just implement an atomic queue for you. So you will have to implement a queue if that's what you want in software, meaning you will have to write a procedure for how to enqueue into the software queue, a procedure for how to dequeue from the software queue, And then, I mean, if any process wants to enqueue, that process will execute the enqueue procedure, and that procedure will do several actions on several hardware memory words, and ultimately say the enqueue is complete. So the enqueue operation, therefore, is this entire execution of the procedure that is meant to implement the enqueue operation, and therefore the enqueue operation is no longer atomic. It's not instantaneous. It spans over an interval of time. Are we together? Likewise, if you want to dequeue, you will execute the dequeue procedure, and that too spans over an interval of time, because the dequeue procedure may involve performing several actions. Okay. So, in the phase of concurrency, when you have a software queue, for example, and several processes are applying operations and enqueues and dequeues concurrently, and therefore their operations are all overlapping, concurrent. In the face of all that, how should a queue behave? For instance, take this execution run. Here we have 3 processes. I'll call a process pi 1, pi 2, pi 3, 3 processes. This is the timeline, and process 1 did an enqueue. It enqueued 1. This is let's say the time at which the enqueue operation started, and this is the time at which it completed. Sometime after that, it called a dequeue. Process 2 has completed 2 enqueue operations, and process 3 has issued and completed a dequeue operation. Let's say this is what happened, but did I completely describe what happened? Not yet, because I told you that the dequeue operation completed, but I have not told you yet what it returned. I have not told you yet what that dequeue returned. Now I am telling you. Let's say this dequeue returned 2 and this dequeue returned 1. And suppose the queue that they implemented exhibited this behavior. Would you consider their queue a good queue or not a good queue? Are you happy with this behavior, or are you not happy with this behavior? I'm not able to hear all of the things that you said, but maybe some other people are, so that's fine. But I'm most interested in the following final juicy outcome. Are you happy with it or not happy with it? You are happy? No. No. Okay. Okay. No. Okay. Is anyone happy with it? Oh, some people are happy with it. Okay. So it's nice to take a poll. How many people are happy with it? Okay. About a dozen. Happy. Yeah. Okay. I see about a dozen. How many are unhappy? A few. And some are still making up their mind. Okay. My question was ill-posed. When I ask, are you happy with me or are you not? What's the criterion, right? We have to first spell out what our criterion is, and then if it fulfills that criterion, well, you should be happy. If it doesn't, you should be unhappy, provided you agreed with the criterion, of course. So I will tell you what my criterion is. The credit for coming up with this criterion doesn't go to me. It is it's the definition of linearizability that Herlihy and Wing gave back 33 years ago, their journal paper, conference even more. And the criterion is this. Well, let me have the satisfaction of saying it rather than just putting it up. So even though each operation spans over an interval of time, you would really wish that operations were not like this and that they are instantaneous. But you are not able to realize that. So if you are not able to realize what is best, then what do you want to do? If you are not able to realize what is best in your life, in my life, what do you think I do? I dream that. I spend half of my life in dreams and half of my life in so-called reality. So how does it matter whether the best thing happens to me in the awakened 12 hours or in the sleepy 12 hours? It hardly matters. It's the same thing. So same thing here. You really wish that operations were instantaneous, but you cannot get that. So how about instead revising your wish to be the following? Even though each operation is not instantaneous and spans over an interval of time, it must appear as if each operation takes effect instantaneously at some point within its interval. Okay? So it's not instantaneous, but it should appear as if it takes place instantaneously. Where should that instant be? Anywhere in its interval between here and here. Likewise, this operation should appear to take effect instantaneously at some point within its interval. So if you can manage to do that, then you say, so if that criterion is satisfied, you say this execution, this run is a good run. It's a linearizable run. So each operation must appear to take effect instantaneously at some point between its invocation, meaning between its beginning, and its completion when it ends. Are we together with what this criterion is? You might say, I understand the criterion, but why is it a great criterion? It's a great criterion because we know that the best thing you can aspire for are atomic queues. But if all you have are linearizable queues, not atomic queues, it turns out linearizable queues are as good as atomic queues in the sense that you can use them as if they are atomic queues and your application would still be running correctly. Right? So linearizability, therefore, is a great criterion. It is atomicity for all practical purposes. Are we together as to what this criterion is saying? Now, let us see whether, let me phrase my question again. With respect to this criterion, do you now agree that this is a desirable behavior? Indeed, it is. Because suppose these operations, suppose they took effect at the instance that I marked here, then it is as if NQ1 took effect, so the queue now has 1. NQ2 then took effect, the queue now has 1 followed by 2. The DQ took effect, so it of course removes the front element, which is 1. That explains its return of 1. And NQ3 then took effect, the queue now has 2 followed by 3. And the DQ then took effect, and it took the front element in the queue now, which is 2. And so the whole execution, the whole history, the whole run is explainable. It satisfies linearizability. Are we together as to why that behavior is okay with respect to that criterion? But what if instead this fellow returned 1 and this fellow returned 2? Is that linearizable? Yes. Yes, it is, as this linearization shows. So now suppose these operations took effect in the following order. This at this instant, this at this instant, so Q now has 2, 3, and then this returned, this DQ got the 2, which is at the front, and then that, and that DQ returned 1. So this is again a fine execution. It's a, huh? Oh, did I?
Yeah, because the second DQ should return 3, so you have to move the linearization point of 3 later after the
I see.
linearization point of the second DQ to make it correct.
I see. Okay, the animation went wrong. But you agree that the dots could have been placed differently to show that that's a fine linearization? I'm glad there was a mistake in the slide because that's what brings us all to life and enjoy it more. I'm grateful for my son. Conveniently put it on him. Okay. What about this? 3, 2. No longer will I say anything. I'm not confident of my animation anymore. This is fine?
Yes.
Yeah.
This is correct.
Yeah, very good. How about this? Return 3 and return 1. Return 1, return 3. No. Because this NQ3 is happening strictly after NQ2. So there is no way to So this is not linearizable. So do we get do we now completely understand what it means for an execution, for a run to be linearizable? Okay. And when do you consider an implementation a good implementation? When you have an implementation of a queue, you don't know ahead of time who is going to execute what operation when, right? So you don't know ahead of time what the execution will turn out to be. So you consider an implementation linearizable if in every execution there are uncountably many executions. If in every one of those executions the execution is linearizable. So that is the obligation on the implementation when it claims that it is linearizable. So it is such implementations, linearizable implementations, that we want to design. Why? Because the objects would then be as good as being atomic objects, which is our ideal. So how do you design such objects? That is challenging and therefore interesting. But once you design such an object and you believe that your design is linearizable, how do you prove that it is linearizable? That is the subject of our study today. Okay. So having, let me pause there and see whether there are any questions or comments. If not, if there is any possibility for you to relocate so that these things are visible, if they are visible from where you are, great. Otherwise, if you can come forward, I would appreciate it because I'm going to use it now. So having understood what a linearizable implementation is, to really enjoy this whole thing, let us try to design a linearizable implementation. Okay? So let's try to implement an object of a certain type using an object of a certain other type, where our intention is that our implementation should be linearizable. So see what the fun is. And let's implement if I write like this, then I probably that won't be enough. Is it visible? Okay. So let's implement. So this is just a toy example. Okay, this is just a toy. Read write object O. So what do I mean by that? I want to implement an object O. What operations do I want it to support? Just the simple read and write operations. But you always implement something from something else. So from what kind of an object do I want to implement it? Let's say from a read cas object X. So X is an object X is an atomic object that supports two operations, read and cas. Read, you know what it does. Read returns the value of X if you execute read on X. But what does a cas do? So if you have not encountered cas before, it's a very simple operation. If someone says, let's say currently X has the value 5, for example. If someone says cas X comma 5 comma 10, cas stands for compare and swap. So this operation compares this first argument 5 with what is already in X. If they tally, if they agree, then this value is removed and the 10 comes into X. Okay? So the 5 changes to 10 if this argument agrees with the current value of X. And so you call the cas successful because it was able to swap 10 into X. And just so whoever issued the cas command knows that that happened, the operation returns true. Just to let them know that indeed there was 5 and it got changed to 10. On the other hand, if at the time you do cas x 5 comma 10, if what was in there is not 5, it's something else, then this operation will leave the value of x unchanged. It will remain at whatever value it was, and the cas operation returns false, so that whoever invoked the cas operation would know that the cas operation had no effect on the object. Are we together? So let us say we have a variable x that supports read and cas operations. Using that variable x, I want to implement an abstract object O that supports read and write operations. And how do I do that? Let's do that. Okay. So okay, I want us to do this together. So I want your suggestions. So let's implement O.read. Remember that you have that x. So just read what is, are you able to see both? Okay, I hope. So here is the idea, right? I mean, the idea is let us ensure that at all times the value of the abstract object O is maintained in x. So if you want to read this register that you are implementing, this object that you are implementing, where do you expect to find the value of O? In x. So you just read x and return it, right? Read x into some local CPU register and return it. Fine? As simple as that. The more interesting thing is the write operation. What shall we do now? Write. But then x does not support the write operation. Try to cast. Try to cast what into what? I'm trying to write the value v into x. So the only way I can change what is in x is through the cas operation. But the cas operation, the nature of it is I have to say if x has this, then change it to v. So read. Very good. So read. So first read x. Read x. What am I trying to achieve? I'm trying to write v into, I'm trying to write v into x. So if x is v, if what was in x is already v, then there is nothing to do. Agreed? Then there is nothing to do. So if x is not equal to v, then I will be telling myself, oh, I want to get my v into x. So what do I do now? I cast into x what? I knew that it, I mean, I am under the impression that it has little x. So if it still has little x, I want to change it to v, right? If I am lucky, this cast will succeed, and I have accomplished what I wanted to accomplish, namely get my v into x. So I am done. Agreed? But if I am unlucky, what might have happened? Yeah, if I am unlucky, my cast would have failed, because since the time I read little x from x, somebody might have changed it, and therefore my cast could have failed. And if it failed, what can I do? If it fails, I can go back and try it again. I'll come to you. If I fail, I could go back and do it again. Are we happy with this algorithm? This is, I mean, that's not a trick question. This algorithm is fine. This algorithm is fine. Eventually, when you succeed, you won't repeat it anymore. You will simply return acknowledgement. Write returns acknowledgement that it's done. So does anyone dispute the correctness of this algorithm at a very intuitive level? We are not asking for any proofs. Huh? It's not life. Yeah. So just with your gut, you can vote happily one way or the other. And no rigorous proofs, nothing, and it's of course not life. Life will never be thus. I keep telling my students, computer science is interesting, you all work hard, all that is fine, but this is just a small facet of life. And computer science is for our life, and our life is not for computer science. So I'm so glad you asked. I'm wholeheartedly with you on that. Okay, coming back.
Do we consider the ABA that is changing back and forth?
That can happen.
And it
Doesn't matter. Because if you succeed, you planted the V. If you did not succeed, you made no difference. So you're trying again, so you are harmless. I'll come to you in just a minute. I think I know what you're going to say. That's why I'm delaying you. But I'll surely come to you before I say anything. So we are all happy with this algorithm. Now I go to you.
I mean, you can just keep it if you fail to cast, and it's still be correct.
Very good. Very good. I knew you would say that. So what we have on the board is correct, but here is something much smarter that we could have done, which is you read X and then you try to cast. If you succeed, of course you are happy and you can quit returning ACK. If you fail also, you can say I'm done and you return ACK and go. Why? Because let's say this is the timeline. Let's say this is the place you read X into X. And let's say this is the place when you did the cast and then your cast failed. If your cast failed, what does it mean? Someone else had a successful cast between your reading of this and your cast. Agreed? Someone else had a successful cast. And who was that someone else? Some other writer was successful. If some other writer was successful, and this is your write operation, it started here and you are here, could you not pretend that you also wrote just before that other write, and then that other write immediately overwrote your write, and therefore you pretend that your write has taken effect? Agreed? I'll come to you. Even if it fails, you don't have to repeat. You can just return the ACK and you go away. So there is no repeat. There is no waiting. You just do 2 instructions and you are done. So that would be a correct implementation, a linearizable implementation. Okay? So linearizable implementations can be very clever. This is just a very small toy example. No one in the right mind would ever have to implement. I mean, any hardware supports read and write operations. So you won't support this. I mean, who would want to? So this is just a toy problem. But this illustrates the beauty of the design of linearizable algorithms. And what could lie? I mean, there is some complexity that's lying behind even the simple algorithm. How would you prove it correct? We will get to that later. But that just gives you a flavor of how a linearizable implementation might be. Please. Okay. So you are suspicious of the correctness of this algorithm. You're probably thinking, I'm not just suspicious, I'm convinced it's wrong. One of the two. At a minimum, you are suspicious of this algorithm. And that's good. That's what I want you to. That's the state I would like us to be in. As you can see, it's a simple algorithm. And then I'm presenting an argument that it is correct. And I think some people seem convinced by my algorithm, and probably some others are not. For instance, you are not convinced. So if that is typical of even a simple algorithm like that, you can imagine what happens if you present a more complex algorithm to me. I could be thinking it is incorrect. Someone else could be thinking it is correct. You present a proof, but then I find your proof hard to read or hard to comprehend. And then, so So there is a need for rigorous proof. There is a need for machine certified proof. Excellent. But from my side, I contend that it is correct, and we will use the break to understand each other deeper on that. Okay? Yeah. So anyway, I'm quickly displaying that algorithm here, but let's move on to another algorithm, which is much more challenging, very difficult to wrap your head around this. So in this algorithm, you are implementing a queue. You are implementing a queue, and you are implementing a queue using the following atomic objects. You will use an array to store the values in the queue. Okay? So this is an infinite array. This is an infinite array, and at each location of this array, at ai, for any I, what can you do to the location ai? You can read it, you can write into it, you can swap into that. For instance, if I say swap 5 into location 10, what will happen is 5 will go into location 10 of the array, and what was in the array will be returned to me. So if the array location had 8, and I say swap 5 into that location, that array location will now have 5 as its value, and what was in it, namely 8, would be returned to me. So that's the swap operation. So let's say you have an infinite array that supports each location of which can be read or written into or swapped. And in addition to that, they use one variable x, which intuitively, which points to the next location in the array that's free for storing the next q value. Okay? So it's pointing to the location that is just past the last location storing a q value. So therefore, you have the array A starting, let's say, with location 1, 2, 3, and what does x have? X have, if x points to the location 5, what does it mean? It means that the first 4 locations were previously claimed and used, and the next location to store a value into would be the location 5. So that's the representation. So now tell me, what do you believe NQ should do? So if you want to NQ a value, what would you do? Suppose you want to NQ a value V. What would you do? X simply has the location, so it has the index of the array where you can write next. By the way, I think I forgot to say one thing. So x is a variable that supports read, so you can read the value of x. It also supports the fetch and increment operation. What does fetch and increment operation do? If you suppose x has the value 5, if you say fetch and increment, then 5 will be returned to you, and that value will be incremented to 6. So x will change from 5 to 6, and the previous value 5 would have been returned to you. So that's what the fetch and increment operation does. So assume that x supports fetch and increment operation. So if you want to NQ a value v, you want to put it into the next free location. So do fetch and increment of x. That will give you this location as well as bumps it to the next place. And so do fetch and increment of x and get that value x. So conveniently it went there so that if someone else is going to claim the location next, they will get a different location, the next location, and you got this previous location. Whatever location you got, you put your value in there. Agreed?
X is non-decreasing, right?
X is non-decreasing. And your array is infinite. You assume it is infinite. Okay? So that's the NQ operation. Clean and easy? Okay. So life has to be somewhat tough at some point. What do you, and it's not that tough either. What do you think DQ should do?
You need one more x.
So first read X. Suppose you get, I mean, let's say a lot of things have happened and it's now 500. Okay, you read X, it's 500. What does it mean? The first 499 locations were claimed previously. From 500 onwards, it's free. I mean, there's nothing in the array at the moment, right? So you know that stuff, you are looking for stuff to find and return. So you know you need to search in 1 through 499. Agreed? Okay, so how do you, in what order do you want to read? Well, Q is first in, first out. Earliest item should be grabbed and returned. So it probably stands to reason to read from location 1. So you read X, you got 500. So you have made up your mind that you want to read through the locations 1 through 499. So you read them. You read them. When you read them, you have to be careful. I mean, suppose there is a value here. You want to grab and return it, right? But if there is a value, you want to grab and return it. I mean, it should not be the case that you are looking for a value here, I am looking for a value, both of us find it and both of us return it. That should not be allowed. So you use the swap operation. You swap, I mean, initially the arrays would have some special value, let's call it bottom. So you swap the value. So if you get a real non-bottom value out and you swapped bottom into it, so you did two things at once. You put a bottom there and you got out, extracted the value that was in there, which you can now return. Agreed? So you swap bottom, but suppose when you swap bottom, you get a bottom back, which means what? That there is nothing in that array location. What can be two different reasons why there is nothing in that array location? One reason is somebody claimed that location to put their value, but after claiming that location, they became very slow and have not put their value yet. And that may be the reason you are finding the location to be empty. Agreed? Another reason is they had put something in there, but some other DQer came and already stole it. So there are two reasons why, I mean, you could find a bottom in some location. But again, you got 500, you are searching through 1 through 499 by swapping bottom. If you get bottom back, that means there is nothing there, not promising. So go to the next location, swap bottom there. If you find nothing there, go do bottom. If you find nothing there, go do bottom. And when you do bottom, let's say you got 8 back and you swapped bottom, but you got 8 back. Then what you do? You return 8. Understand? Okay, so that's what they do. But what if the following happens? You read 500, you search through 1 through 499, going through each location and swapping bottom. But you went through all 499 locations and you found nothing in any of those places. Then what should you do? Then what should you do? What do they do? What they do is they say, oh, okay, I was unlucky. Let me try again. Let me try again. So they will read X again. In the meantime, X could have changed because many NQers came and advanced it. So if you read X now, let's say you get 800. Now you say, okay, I'm going to patiently travel through 1 through 799. And you do the same thing. You do the same thing. At some point, if you get a value out, you return it, you are done. But if 1 through 799 turned out to be empty and you are unsuccessful, what do? Read X again, which now might be a million. Now go through 1 through million minus 1. Is the algorithm clear? That's it. That's the algorithm.
What's the reason behind exploring all the previous variables again and again, or not to
what is the point in repeatedly exploring the previous ones again? Because the following is a possibility, right? I was an enqueuer, I grabbed the location 2. After grabbing the location 2, I have not put a value yet into 2. So maybe the first time when you went through, because I had not put anything there yet, you didn't find anything there. But maybe if you look for it again, in the meantime, I might have put something there, which, I mean, in your second traversal, you might find.
I mean, why not to have second pointer?
Huh?
Second pointer for the beginning of your queue and the end of the queue. Not to have only one, or it's the basically that you can't have more.
I see. Just as you have the last to, why can't you also have a pointer that says it's pointless to search the area before?
Yeah, this is the question. So if it's preconditions, okay, then I'm game.
Because, okay, I'll answer it in 2 parts. First, I'll answer you. And the second thing I'll tell you. Nobody knows, I mean, suppose these 3 are blank. Okay? Suppose we all see and that these 3 are blank. Can we be sure that nothing ever will enter any of these 3 spots? We cannot be sure. Because there could have been someone who is not friend of ours, who had gotten this location and then was going to put something into that location, but has gone to sleep. Okay? So if all of us see bottom, bottom, bottom here for a million years, we cannot be certain that nothing will suddenly show up the next moment. Because, right? So I can never give up on these 3 locations and say, all in the future, you all please search only from 4, because these 3 have been bottom for a million years. I cannot be sure of that, because some other process that grabbed this location but has not yet had a chance to put something in there might wake up in the future and put something in there. Therefore, they do not use a front pointer. So that's the real answer. Another answer is, at this point, I mean, let's not even care about whether there is a smarter algorithm or not. Let's understand what their algorithm is and see whether it's correct. Their algorithm is what I just told you. Yes?
If I know that I earlier has DQ'd something from number 2, so I could have used that already.
Yeah. Instead of putting the same initial value bottom, if I put a different value there, like a $sign, for example, that would have helped us understand if there are $3 here, we know that they were already removed, and therefore you could start from here. But then here we are not looking for any efficiency. This whole algorithm was presented to make a point that algorithms can be very complicated and linearizability can be accomplished in very clever, smart ways, and we have to be aware of the innumerable possibilities that it could generate. Yeah, so the whole point here that they were trying to make is not coming up with an efficient queue implementation, but something to illustrate several points related to linearizability. It was in the paper on linearizability that they used it as an example, but it became a very famous example because it really brings out how hard it is to prove linearizability. So this is the algorithm. Okay? So in particular, I'll tell you one scenario. Suppose as you use this queue, the following could easily happen. That there is some location here that has some value, let's say 5. Some location here that has some value, let's say 1. And there could be a million empty locations in between. And some location here that has nothing. Meaning it has bottom. And let's say x is pointing here. And you can visualize many more values being present in these earlier locations before x. Now, if anyone asked you what would be the next value that would be returned by a dequeuer in their algorithm, it could be any one of these values. The next value that will be returned by a dequeuer can become any one of these. You can create scenarios in which any one of these is going to be returned next by a dequeuer. Okay? So, you cannot make up your mind firmly as to if it is in this kind of state. I mean, is 5 going to appear before 1 and in the abstract queue, in the implemented queue? You can never be sure. Any one of these could be appearing first. You can create such scenarios, and that is what leads to that complexity. So, where are we? We are at a point where we understand that judging the linearizability of an algorithm can be very difficult, because if you want to claim that an algorithm is a linearizable algorithm, what do you really have to show? You have to show that for every run, for all runs, and how many runs are there? Uncountably many. There exists a linearization, meaning there is a way of putting these points. And in how many ways can you put those points? Uncountably many ways. And it's non-constructive. It's not like I know how to put the points for the first 5 operations, and therefore when the 6th operation returns, I know where to put the point for it. There is no such thing. So, for all runs, of which there are many, you have to show that there exists a linearization, which is non-constructive existence, and that is very, very hard to prove, and therefore a pen and paper proof of such a thing is often, can be, often is a strong word, but can be slippery, can be buggy. It can be too long, too tedious to write in detail and to verify in detail. And so that's where we are, and thus that necessitates our goal, which is to come up with machine verified proofs of linearizability. Okay, so let's stop there. I think it's a good point. We will now, after the break, we will see the theory as to how to do it.